Welcome back. We're now going to look at a couple of examples, right? As we were chatting off I don't know if we call it off air, but what we're saying is we want to add a few more, but we'll do that as added content when I've gone through these problems here. Now, let's have a look at a problem. First of all, they say a vehicle of mass 2,500 kilograms. So we've got a vehicle of mass 2,500 kilograms. Travels at 32.4, V equals 32.4 kilometers per hour. Already you can tell that's not going to be cool. Why? Because it's in the wrong units. Okay, it's got to be meters per second. Next I'm going to say at point A. So this is at A. That's at A. Let's make A a little bit neater, shall we? That is at point A. All right? And accelerates over a distance of 500 meters to 57.6. So already I've got that, and we've got V final equal to 57.6 kilometers per hour at B. So right now, like I've said to you guys, we need to draw it. So let's say that's A, and that's B, and at this point my vehicle is traveling at 32.4 kilometers per hour, and it takes 500 meters. Now that's delta x, isn't it? Right? It does that to 57.6, and at this point it's 57.6 kilometers per hour. Right, how do we change those? Simple. We say, right, I need to change kilometers per hour to meters per second. How do I do it? I times by 1,000, and over here 3,600, and essentially I times by 1,000 divide by 3,600, and if I do that I get velocities of 9 meters per second here, and over here velocity of 16 meters per second. Then they tell me that against a uniform friction, and they've given mu k equals 0.4, right? Now the moment they give mu k, what do? I say I put my FW, the weight here, is going to be equal to mass 2,500 times 9.8. That is going to be 24,500 newtons, correct? The mass stays the same. I'm not going to put it in twice. Therefore, F normal is equal to 24,500 newtons as well. Therefore, frictional force is equal to mu F normal, and it's kinetic because it's moving, remember? So it's going to be 0.4 times 24,500, and I believe that's 9,800 newtons. And it's a uniform frictional force. And let's go back to what we used to do and put in FF equal to 9,800 newtons of frictional force. Okie dokes, there we go. We've put it in now. Now let's have a look. So what can I say? First of all, I say, okay, they've given us the mass and we know the velocity, which means we can work out EK final and EK initial, can't we? So I say, all right, therefore EK initial and EK final. Remember we said in the recipe, put all the forces, put in what you're given, and then look at the EK, right, and see if you can work out anything. So EK initial is going to be a half times 2,500 times 9 squared. EK final is going to be a half times 2,500 times, I think, 16 squared. Let's write down some numbers. 320,000 joules, that is. And the next one is going to be initial energy. Where are you? Ah, yes, is 101,250 joules. 101,250 joules, right? Therefore, I can say, what is the change in kinetic energy? Because what they want to know is they want to know the work done by the engine. So let's just write down, what are we targeting? Okay, work done by the engine. Okay, now let's just think, just hold on. Before we go any further, what does that engine have to do? The engine has got to drag this vehicle or this object, here it is, here's our truck, it's got to drag this object against a frictional force. So there's a work done to overcome friction, and if it's increased velocity, there's extra work done in increasing the velocity, isn't there? So there's the energy work done by increasing the velocity and the energy to overcome friction. Essentially, that's what we're saying. That's the total work done by the engine, isn't it? So let's have a look here. Okay, so what did we know? We know, hang on, F net delta x, we know that F net delta x is equal to delta EK, don't we? Right? And we know delta EK because this is final. So it's 320,123 minus 101,250, which is equal to how many joules? We know that is, let me just check, is going to be, let me just put on my calculator here, just so I've got it, is 320,123 minus 101,250 is equal to 218,750. 218,750 joules, right? Now, that's going. Now, let's have a look. We said F net times 500. So therefore, F net times 500. Therefore, F net is going to be equal to 218 divided by 500. Divided by 500 is going to be equal to 437.5. 437.5. And it's a force. So I now know what F net was, right? We've got it. I'll show you, we'll have a look at something else in a minute. So we say, okay, so therefore, let's have a look, all right? The F net was that. What is then the other force that's necessary to overcome? The friction. So therefore, remember, F applied, okay, is equal to 437.5 plus 9800, which is going to be equal to 10237.5 newtons. Therefore, the work done is going to be 10237.5 times 500, which is going to be equal to 5118750. 5118750 joules. Right? Because that's the force to accelerate, and that's the force to overcome friction. Right? So therefore we had to have a force to overcome friction, and we had to have a force to accelerate. That is how we do it. Okay? Not that mentally challenging, not if you follow the recipe. Look at what we did. We put down the information, I drew it. I said, here's my car at A, here's my car, truck, whatever it be. Put in what I know, changed my units, right? Then we went through and we put down, what can I calculate? EK. We did it. I then just applied the formula. F net delta X is change in kinetic energy. And we have the answer. All right. Let's just move on. All right. Then we say we can check, all right, using Newton's laws of motion, Newton's equations of motion. But in this case, they didn't want us to do that. All right. Let us have a look now at another problem. Okay. We've got the truck now climbs a hill. All right. It now climbs a hill as shown. All right. I just want to put this over here. Bear with me a sec. It now climbs a hill, come on, as shown. And they have said to us that this hill looks like that. And they have told us that it climbs 60 meters over 1,000 meters. Okay? Rise over run, for those of you who are doing geography, basically you can calculate theta over here if you want to be a purist. Okay? And it's going to be shift tan 60 over 1,000. I always recommend do it. Do it. Okay? Because you're used to working with theta, if you can, calculate it. So that comes to 3,43 degrees. Now we said the truck, all right, previously it weighed 2,500, remember? So it was, this is 2,500 times 9.8. This is FW, which is equal to 24,500. Okay? And now what did we do? We now broke this up. I'm just using a bit of color here. Huh? So then I said that's 3.43 degrees there. So I work out what my mg sine theta, my mg cos theta, and that gives me my F normal. Mg cos theta is going to be equal to 2,500 times 9.8 times the cos of 3.43 degrees. That's going to give me a total of, let me just check, 24,365.8. I just want to check, 365.8 newtons. Okay, that's my F normal now. Right, what do I do next? Next I say, okay, hang on, I bring this guy down here. Mg sine theta is going to be, I don't need to work that out, it's going to be 24,500 times sine of that, all right, is going to be, hold on, let me just check myself, 24,500, which is that, mg times sine of 3.43, which is equal to 1465.8. 1465.8 newtons, right? Now, there's nothing else that we've done differently. Then we said, right, there's an F applied, because they say they want the work done to maintain a constant velocity. F applied is there, nothing new. It's going up the hill, so let's go back. FF, okay. Now remember, it's equal to mu 0.4 times 24,365.8, which is, in this case, going to be 9,746.31 newtons. Okay, I guess that's really doing splitting hairs, isn't it? But please remember, as the slope goes, your F normal changes. So all I've done is I've said that I'm using the same coefficient of friction, but the frictional force has got slightly less. All right, 9,800 to 9,746. I'm being a purist, I guess. All right, so now they say, well, straight away, hang on, I know the difference in height here, don't I? So I can work out the EP at the top is going to be 60 times 9.8 times 2,500 is going to be mass GH. So my gain in EP is 1470,000. 1470,123 joules. There we go. Okay, I've just worked that out. They want the work done by the engine. Okay, well, now let's have a look. Okay, so the work done by the engine. Okay, now remember they wanted this. I'm actually going to write it in red, at constant velocity. Please remember, we could have done this with an acceleration. In other words, I would now introduce a change in EK. But at constant velocity, therefore, delta EK equals 0, because F net equals 0, right? Then the last thing, then what is F applied, right? Constant velocity, therefore, F applied must be equal to 1465.8. That plus that. Plus, and my friction 9746.3. So my F applied is 112.11215.1 newtons. Okay? Therefore, the work done by the engine, let's go back to black. Therefore, the work done by the engine is 11215.1 times delta x. Delta x is what? Delta x is it's this distance, isn't it? To the top of the slope. That is the force applied acts over that distance. So therefore, it's going to be that times, and it's going to be times, but what is the distance? Well, delta x squared is going to be equal to 60 degrees is 60 squared. Come on. 60 squared plus 1,000 squared. Therefore, delta x is going to be 1001.8 meters. So times 1001.8, and my final answer is going to be the work done is 112.287.2 joules. That's the work done by the engine, right? Let's just check on something. Delta EP is going to be what? mg sine theta delta x. Remember my formula? mg sine theta times delta x. NB, remember it, which is going to be 2,500 times 9.8 times the sine of 3.43 times 1001.8. And if we work that out, we get the following. 1468, 450 joules. Okay, straightforward. Now hang on, I calculated EP 1470. Remember? Okay, 1470 joules like that. Okay, so, well, there we go. That's kind of the same number. The reason for the difference, by the way, is it's not 3.43, it's 3.43 something. So we're going to get a slight rounding error, which is magnified by multiplying them by large numbers like this. Okay, now that pretty much deals with those. Oh, hang on, calculate the power used, all right? And I haven't talked about power yet, but power is equal to work done over time, and it's measured in watts. We're going to do more on power just now. But hang on, I know they want to know what the power of the engine is. I say, well, it's 352.87.2 is the work done, that's joules. Joules per second is power. What's the time? Hang on, time. How do we work out time? Okay, well, it says constant velocity, right? So therefore, we said that it's traveling at a constant velocity of 16. Therefore, we can work out velocity is delta x over delta t. So therefore, we've got 16 is equal to 1001.8 over over delta t. Therefore, delta t comes out to be 62.61. So divide that by 62.61, and my answer is 179,448. And I think we can call that 179.4 kilowatts. You asked me, the truck basically carried on from the previous example. That's where the 16 comes from. I should have actually mentioned that. It's the same thing this character here, okay, had a 16 meter per second, remember? From the previous example, it was traveling at 16 meters per second at this point, and now it goes up a truck, it goes up a slope, right? So what we're saying is we're saying our truck's moving along, it gets there, then it goes up a slope, and they want to keep it going at a constant velocity of 16 meters per second. My bad, I should have explained that right in the beginning, but I'm sure that you've sort of picked it up at this point now. Now, all in all, there's just there's going to be a few more on these energy problems as well that we're going to do. Vertical motion, I'm going to do in the next section. Just let's have a look, for example, at this one, right? Just as a quick sort of look just as we're ending off over here, all right? What if I, for example, had the truck starting at the top over here, and let's say it's traveling at 5 meters per second, and we want to get to the bottom at 10 meters per second. There's a nice example in one of the exam papers that I've seen with this one where there's an arrestor bed. I'll do something like that, but let's look at it in concept, right? What are we saying? We're saying that we have a change in EK. Hang on, there's a delta EK, which must be equal to what? Oh, F net times delta X. So I can calculate delta EK there, can't I? Right? And I say F app, because I know I'm going to do that. What's acting back over here is FF, force of friction, isn't it? Right? And acting down here again is my mg sine theta. Can you see it's the same forces all over and over and over again? We're only working in one dimension here, right? Thank goodness, I suppose. But that's what we've got. Force of friction's acting up. So in this case, right, F net, okay, is those two minus FF, isn't it? Can you see it? Acting down is going to be F app plus mg sine theta minus FF, all right? Remember, I'm actually doing it from I guess from a basic point of view here. I'm trying to keep it simple, stupid, all right? I'm not looking, what I've seen with some of my students is they've got a formula, whether it be whatever, conservation of energy, that must equal that, and they just plug it in. Well, you can't, because you have to actually look at which way things are acting. I am actually accelerating down the hill here. So there's my F net, and my delta X must be equal to delta EK. All right? And the same applies, mg sine theta delta X is equal to my change in potential. But what's actually happening here? My EP is dropping. So I'm going to get a negative EP, aren't I? What's actually happening is that potential energy, as it's sinking away, is actually helping us to increase the velocity. Is that not so? Think about it. Okay? What's happening here? Let's think about it from an energy point of view. Here's a ball. Boom. The potential energy of that is there. What happens? The potential energy gets converted to kinetic until it hits the bottom, right? Where that's the maximum kinetic energy at that point. So where we are is we're now moving down a slope, and we just apply it in exactly the same fashion, right? No, you don't have to go and do anything else. Just the same way. I like this method. It makes a lot of sense, okay? It's versatile. You can approach any problem with it. And it's basically, you don't try and plug it into formulas. Obviously, you know what the formulas are because you're going to be using them at the end of the day. All right? There we go. So what I'm going to do now is the next one I'm going to be looking at is the work energy theorem. We're going to do something on power. And let's see, some vertical projectile motion as well with these. All right? Where we've got things going through various bits and pieces. Okay? Air resistance will come into it and things like that. But Don't worry, there's going to be one or two more that I'm going to add in as well, because this section we need to do a few more typical examples just so that you're comfortable with it. Cheers. I'll see you in the next one. Bye.